Welcome to the video Toughness, the KQ and the KEE criteria. The measurement of toughness as a material property is something that is not easy. It's not always easy with a ductile material because it is difficult with ductile material to guarantee the small scale yielding condition. For this, we have values that are coming from a real E992 valid measurement and data that are coming from conversion of J measurement. On the other side, we cannot increase too much the specimen thickness because it could be not a representative of our material. Imagine a wall thickness of 100 millimeters, 75 millimeters, when the casting is 25, for instance, or 50. And so we are obliged to use compact specimen E992 of a size that is for us acceptable at 45 millimeters or lower, and where it's not possible to guarantee for all materials a small scale yielding condition. For this reason, we tried to use an approach that is of a normal process control by an important manufacturer of railway wheels, forged railway wheels. And this approach is given by a standard specimen, a size of 30 millimeters, that is tested using an E992 procedure and not respecting the small scale yielding, but where it is measured at the PQ, so the load where the curve is no more linear, and also it's measured the area of the testing curve up to the maximum of up to the maximum load. Then, from the measurement of the area under the curve, it is calculate the so-called PEE. So the load corresponding to the same area on the linear elastic trend of the triangle, this area being equal to the area of the testing curve up to the maximum. And from the linear elastic formula of the CT specimen, these loads are converted into K, called KQ and KEE, that means energy equivalent. This procedure of calculation KEE is not based on the actual valid standard procedure, but is based on an obsolete standard procedure of many years ago. But anyway, we believe that using this criteria, that I repeat is in common use in the railway sector for the forged wheels, we believe that we can adopt the same criterion for comparing different materials. We know that this comparison is not made on material independent properties, but is something that is depending on the specimen size. But anyway, as it happens with the Sharpie, we compare conventionally in these conditions the different materials. So to have an idea of when this material is has a behavior that is no more linear, the KQ, and also how much energy it can sustain before to enter into the unstable crack propagation. So it is something that we can use for ranking. And so with this procedure, we tested some of our materials, as you will see now. This is the test of an ADI, a low-grade ADI, an ADI 800 ultimate tensile strength megapascal. This one is a test of an IDI, an isothermal ductile iron. This test is given for a 3.5 silicon ferritic ductile iron, so the 514 grade. And this one is given for the highest high silicon ferritic grade, the 610 with the 4.3% silicon. In this slide, the results are shown all together, and the white dots represent the ferritic high silicon grades. On the left, you see the 3.5 silicon, the 514. On the right side, you see the highest silicon, 4.3% silicon and grade 610. The lower dots represent the KQ values, and the upper dots represent the KEE values. So you see that the 514, the 3.5 silicon, has a KQ value that lies on the small scale yielding maximum value that we adopt as reference, and while the KEE values are above this limit. On the right side, you see how the high silicon 4.3 and 610 grade shows how the KQ value and the KEE value are both below the maximum small scale yielding curve. And this requires attention for the designers. Then you see that on the same range of yield strength, we have the IDI, the isothermal ductile iron materials, where we have the KQ values are approximately in the range of the small-scale yielding maximum, while the KEE value are well above those expressed by the 514 ferritic, high silicon ferritic. Then you see the IDI, where you can see that the KQ values are on the line of the small scale yielding maximum, while the KEE value are above any other of the tested material and similar to the maximum of IDI. For comparison, we show also in red the KQ and KEE values for a ferritic steel that is in current use for production of railway wheels, and where we see that the KQ values are above those of ADI, and but the KEE values are below the ones measured for ADI. You see that the maximum small-scale yielding, the dotted white, nearly horizontal lines are 2 and not only 1. The lower is for ductile irons, where the Young modulus is 117 gigapascal, while the upper line is referred to steel, where the Young modulus is calculated as assumed as 210 gigapascal. In this figure, we enlarged our point of view, displaying also on the right the behavior of two alloyed, wrought, quenched and tempered steels, and where you see that they have a much better behavior of any one of our tested material. It means that, of course, the KQ values are not far, as happens for our materials. They are not far from the small-scale yielding maximum values, as happens also for our materials, with the exception of the very high silicon ferritic, but the KEE value is much higher than any of our tested ductile iron materials, but also much better than the normalized ferritic steel. It means that with the quenched tempered alloyed steels, we can obtain a safety guarantee for design that is above any other of the material we can provide with ductile irons. And this could be said as a forgiveness aptitude when some calculations are not fully representative of any event the component can be called to sustain. And I believe that this is the real main difference between steel and substituting ductile irons in design. This is the main factor, the key KEE value that we need to know, we need to design for when we substitute from this kind of steel to stamped ductile iron or isothermal ductile irons.